So I'm going to find the magnetic flux per unit length between two parallel wires. The wires have radius A, and their center to center separation is H plus A, which means from edge to edge, the difference is H. And they are carrying current I in opposite directions. The steps I'm going to go through to do this are going to be to draw a diagram. I'm going to write down the magnetic flux density, which I already know from the Bios of artwork that we did a chapter ago. Then I'm going to simplify the problem by doing some symmetry stuff. I'm going to choose a magnetic flux surface to calculate the flux through, and then I will find the magnetic flux per unit length. So I'll start by drawing a diagram of the problem. My problem is, where did I say two parallel wires? Yes, I've got one wire that looks like that. And they're infinitely long wires, so they kind of keep going on forever and ever. And another wire parallel to it. And these wires have radius A. I drew them really small, so it's kind of hard to see what A is. And their center to center distance is H plus A. How am I going to do this? So step one was to draw a diagram. Step two is I know the magnetic field due to a wire along the z-axis. All right, so for right now, I'm going to choose that the z-axis is here going through one of the wires. And if that's the case, then the magnetic flux density due to that thing is going to be mu naught, because we're not in a magnetic material, times the current on the wire divided by 2 pi rho A hat phi. We remember that because we calculated the magnetic field due to a wire when we were doing Bios of art law stuff. And in general, Bios of art law stuff is how we get the magnetic field and the magnetic flux density, because Gauss's law for magnetic fields is not as useful for finding the magnetic field as Gauss's law for electric field is. All right, cool. Now, here's where I simplify the problem. This was step one, right? Step one was draw a diagram. Step two was I know the magnetic field due to a wire. Step three, I'm going to simplify the problem. And I'm also going to sort of choose my flux surface at the same time. The surface over which I'm going to calculate the flux is going to be a little square in between the two wires. Because I'm assuming that the current is flowing on the surface of the wire, so there wouldn't be anything going on inside the wire. And this square in between the two wires is going to have z dimension delta L. And its bounds there are going to go from A to, oh, that makes it H minus A. That's annoying. I'm going to make it H plus 2A center to center distance. So it's going to go from A to, no, that would just make it A plus H. Oh, well, whatever. I guess it's going to go from A to H minus A. So that's only slightly annoying. Anyway, okay. Here's where I do, I see a hand up. What's up? You're muted.
Sorry, I had trouble clicking the mute button. After that arrow, does that say Z?
Right here?
Yeah,
Yeah,
right there.
I've defined that to be my z-axis.
Okay, thank you.
All right, so here's the thing. Symmetry argument. If I choose my z-axis to be going down the middle of this wire, and it's carrying current I to the right in the positive z direction, then I know that it's going to have, if I do the grab the wire technique, the right-hand rule here, I know that it's going to have a phi-directed magnetic field that is going into the board in that region. The other wire, pointing in the opposite direction, right? If I grab that wire, it has a phi-directed magnetic field that's pointing in the opposite direction. I've set up my flux integral now. My flux integral for wire number 1 is going to be from 0 to delta L in Z, and it's going to be from A to H minus A in rho. And that will get me the flux due to wire 1. The total flux is the sum of those two fluxes because the total field is the sum of the two fields, and superposition works. When I'm calculating flux 1, I'm going to put the z-axis over here. When I'm calculating flux 2, I'm going to put the z-axis inside the bottom wire, pointing in the other direction. And then by symmetry, those two fluxes are going to have the same integral. Does that make sense? So when I'm calculating flux 1, I put the z-axis inside the top wire. And then I calculate my flux integral over these bounds. So b1 dot ds. And I have to make sure that in the other one, ds is pointing in the same direction and everything. Then if I move my z-axis to be inside the second wire and point it along the direction of the current in the other wire. So step 1, I notice that when I do this, the magnetic field due to wire 2 is still pointing into the board because it still circulates around the wire in a right-hand rule-wise direction. And it's still A hat C directed. It's just that A hat C now is relative to this z-axis instead of this z-axis. So this one had it like that, and this one had it like that. I'm going to integrate over the same bounds. And my magnetic flux dependence is going to be the same relative to wire 2. I see another hand up. What's up?
Hi, sorry to interrupt. I was wondering, where is H?
Where is H?
I'm a little bit confused. Which part is H?
It's the spacing between the wires.
Oh, I thought that's H plus A.
Well, yeah, so like this distance is H. I guess that should be H plus 2A if it's like that. And then the rho value from the rho value right there becomes H plus A. It's kind of annoying. There isn't an easy way to make this place, the distance from the center of wire 1 to the edge of wire 2 be equal to just H. So it's annoying. But what I'm trying to do is I'm trying to have the edge to edge distance between the wires be H. But what I'm trying to say, and the point that I'm trying to get across here is that if I take this entire problem and I rotate it, like I rotated it 180 degrees, there's no way to distinguish between wire 1 and wire 2. So flux 1 can be calculated exactly the same as flux 2, and all I'm doing is rotating the problem 180 degrees in the plane of the board. So now I have that flux 1 and flux 2 are equal to each other. That is my simplifying the problem step of step 3 and my defining the flux integral step of step 4. The total flux passing through this little square that I've defined is the sum of those two, flux 1 and flux 2, due to wires 1 and 2. So then if I evaluate that, I'm going to say C total is equal to 2 times integral of mu naught I over 2 pi rho dz d rho, and that's a double integral from 0 to delta L and from A to, what did I say now? H plus A. Nothing in here depends on Z, so the delta L can.
Professor?
Yeah.
Is it H plus A or H plus 2A?
H plus 2A between the center of one wire to the center of the other wire, but we're only going up to the edge of the wire, so it's H plus A.
Oh, okay. Thank you.
All right, anything that doesn't depend on the variables of integration can come out. So mu, I, 2 pi, all that stuff comes out. Nothing inside the integral depends on Z except for dz. So I get Z evaluated from 0 to delta L. So I just get a factor of delta L in the front. So far I have that the total flux is multiply this 2 by this 2 and cancel them. Then I have delta L mu naught I over pi. So far so good. And then I'm integrating 1 over rho d rho from A to H plus A. Remember that the integral of 1 over x is natural log of x. So that turns into ln of rho evaluated from A to H plus A, which turns into, I love whiteboards, ln of H plus A over A, the end. And I wanted the flux per unit length. So I take my delta L and I put it over here, flux per unit length.